Okay, sure. Can I start?
Let me introduce you. So
Yes. Okay.
Danilo is so eager to tell us about his work. Hi, everyone. It's good to see you again. I hope that you're having a good last month or so of summer before things start to change. It's a pleasure to have Danilo Rezende here from DeepMind. He has been doing work for, I guess, a year or two now, thinking about generative models and lattice gauge theory and how they play together. And he will motivate all of these things, but it's a particularly exciting direction for ML and physics, I think, because these techniques in quantum field theory are so fundamental, and yet there are fundamental sampling problems that are difficult to overcome. And so what Danilo is going to tell us about is the various different aspects of things we want in various quantum field theories and how to use generative models together with symmetries to make improvements on everything. So it's wonderful to have you here, Danilo. We're really excited for your talk, and I invite you to please take it away.
Thank you very much, Jim, for the intro and for the invitation. So very excited to be giving this talk and the discussions that will follow. So can you say as I change my slides?
Yes. That's great.
Yes, okay, very good. So in this talk, I will go first over some of the basic ideas and recent some not so recent developments in a family of generative models that we call normalizing flows, which seems to be a very good match for lattice QCD sampling. And so I'll go over some recent developments in the literature in this front. And then I'll go over some of our work in this collaboration that we have on flows for lattice QCD. So everything started by modeling scalar fields, right? The simplest thing we could model. And gradually we start increasing the complexity. So from scalar fields, we went to a U1 gauge group. Then we moved to add fermions to the model and try to sample configurations for the Yukawa model. Then we considered more complex gauge theories with UN and SUN groups. And finally, we'll end with a discussion about what are the next steps to incorporate fermions to SUN gauge theories with this kind of models. So what are the necessary ingredients and how far we are from getting there? So start first. This is this great group of collaborators that I work with me, and yeah, it's been an amazing journey with these people working on these problems. So these are the topics. So let's start with this overview of recent developments in normalizing flows. So the idea of normalizing flows generative model is extremely simple. The idea is that we start from a simple distribution, let's say unit Gaussian in the Euclidean space, and then we perform a series of simple transformations, invertible transformations, or a series of diffeomorphisms to this distribution, and then to end up with a more complex density. So that's the idea. So there's nothing particularly complex about this concept, except in the design of this diffeomorphism. So all the research in normalizing flows goes into how we can design this sequence of maps of diffeomorphisms that have the right properties for the problem that we are interested in. So, and the properties involve both the symmetries of the problem or other constraints. So if the data lives in a particular manifold, so these diffeomorphisms have to be diffeomorphisms on the manifold, on the data manifold, and preserve the symmetries. But also there are computational constraints. For instance, we need, in order to calculate the likelihood of this transformed distribution, we need the determinant of this of the Jacobian of these diffeomorphisms. And in general, this is very causes scaling problems. In high dimensions, the computation of determinants becomes very expensive. So we have to be creative in designing these maps in such a way that the computational and memory costs of the determinant does not blow up. Basically, these are the main constraints to take into account. One of the most popular architectures for building flows is what we call masked autoregressive flows, because they are so straightforward and quite expressive. So the idea is, if you have a data vector, let's start thinking in simple terms or in Euclidean space, just modeling a vector. The idea is that we split this into 2 or more groups, and we transform them independently, we transform them independently. So this creates this triangular structure in the Jacobian, as you know, making the computation of determinant linear in the dimension instead of cubic. So this is a very popular mechanism that we can use, and it's indeed most of the models that we work on are built on top of this idea. Now, obviously, we can also think in terms of a continuous sequence of transformations, right? Where each transformation is infinitesimal, and we have to integrate them to have a finite change in the density. So this can be written as an ODE. So this flow is the integral of a gradient field. And the changing density is given by this formula, which is basically the integral of the divergence of the vector field that you're integrating. So this idea, obviously this formula is known for a long time, but this idea became popular recently due to various techniques to make this divergent term efficient to compute. We can extend this idea to non-Euclidean manifolds, to Riemannian manifolds. The formula is essentially the same. The only thing that changes is the divergence operator, that now it has a metric inside. And so in principle, that's the only change. In practice, right, now I have to integrate this ODE manifolds, and there comes with lots of practical challenges to do this. But in principle, the generalization of this idea is quite straightforward. Now, a particular case of this type of flows is what we call gradient flows or Monge-Ampere flows, which are these continuous flows where that are the integral of a gradient field, which is the gradient. So the vector field that's integrated is a gradient field of a scalar potential. And in this case, the formula is the same, except that you can rewrite the divergence term in the Euclidean space as a trace of the Hessian matrix of this potential. And this formulation is very interesting. I'll explain why this is so interesting in a minute. So also very related, but coming from different literature. So this is already from the Lattice QCD community. This is work from the Lattice QCD community. They have also been exploring these continuous flows. And in that context, they call them trivializing maps. But there's something that's a difference that is particularly interesting here. The idea is, if we take a continuous flow, a continuous normalizing flow defined by the gradient field of a potential, and instead of thinking that it transforms from time 0 to time 1, so you think about the whole trajectory of this flow at every time step between 0 and 1, I have a density. Now I want to match this density to a annealed version of my target. Let's say I do some kind of annealing of my target from 0 to 1, and I want to match at every point in time in this interval 0, 1, these densities. If you do that, we can rewrite this divergence formula in a local form, and it looks like this Poisson equation here. So the idea here is that instead of trying to, the idea in the trivializing maps paper is that instead of trying to do some optimization to bring the flow at the last time step close to a target, density that you want to match. The idea here is to try to directly solve this post-time dependent post-on equation with the flow. There's very interesting things that happen in a pure gauge theory, because the action of the pure gauge theory in the lattice is an eigenfunction of this Laplace operator, which simplifies solving this equation. So this paper has some very interesting insights. I think there are obviously limitations. We cannot solve analytically this. Okay, the solution involves is a perturbative expansion on the time parameter, and the accuracy of this solution degrades very quickly with the inverse temperature parameter of the target density. So it's not a completely scalable solution, but has very interesting insights in this idea. A more scalable version of these gradient flows are what we call the convex potential flows. So convex potential flows, the idea is that instead of integrating the gradient field, you take a scalar potential and you define the transformation as its gradient. So this idea comes from a literature that on the field called optimal transport. And there's very good reasons to define the flow this way. So for example, one nice advantage, one nice property of such flow is that they are curve free. So they will not do unnecessary deformations to the density that do not alter the likelihood, for example. The main constraint in building this kind of model is in this scalar function. So it has to be for the gradient field to be a diffeomorphism. The scalar function has to be smooth, but also strongly convex in a convex support. So this is kind of a stronger constraint, but there are some cool ideas of how we can build, for example, neural networks that have these properties, and we can build flows on that. I'll show some results using this kind of flow later on, and they work pretty well. So they have scaling problems as well, but in a low-dimensional regime, they can be made to work. And what I think is one of the most interesting, maybe perhaps computationally very challenging, but I think it's the most interesting and beautiful generalization of this is the generalization of these convex potential flows to Riemannian manifolds. So obviously the concept of convexity doesn't apply to more general manifolds. That's where we use this more general notion of cost concave functions, which are functions of this form in the slide. That is, they are defined implicitly as a minimization involving the intrinsic distance in the manifold. So as you can imagine, for an arbitrary manifold, this can be extremely expensive to compute. But for some manifolds that have simple intrinsic distance functions like spheres, torus, Lie groups, some of the Lie groups, this is still something that is very, very promising. So the idea is that you define this cost concave functions, and you define a diffeomorphism in the manifold as the exponential map of the gradient field of this map. And what makes this powerful is that there is a huge amount of theory behind this, but this is the key theorem. There, will not read it, but basically what this theorem says is that given any two densities in compact borderless manifold, there is a unique scalar function such that the exponential map of its gradient field maps one to the other. So that's pretty powerful result. So that's very interesting, I think. So there are because these things are very expensive, a cheap idea that has come out in the literature is the idea that these functions psi, so we make them discrete basically, And now you have a discrete set of things to optimize over, and you have this kind of piecewise quadratic potential function. So this is an idea that is interesting, but also does not solve the scalability issues of these flows. And for any of this flow, now what makes these things interesting for physics applications, especially fundamental physics applications where we have these known simple symmetry groups, is this result, which is if we have a scalar function in a Riemannian manifold that is invariant with respect to the action of a group, its gradients essentially commute with the action of the group. So that is, the gradients, they are equivariant with respect to the group action. So we can use that to build invariant complex densities that are invariant with respect to the action of some group. And this is also a very general result. So this result combined with this all these ideas to build this continuous or gradient-based flows form kind of very powerful set of tools. Now, if you are thinking about how to use these things, so the typical applications that I have in mind here are applications where we have some target action or energy, which is a unnormalized probability, which defines a unnormalized probability. And ideally, we should be able to optimize that only using samples from the model, because, well, if you could sample from this target from the target action, we wouldn't need the model in the first place. So that's that would be desirable. Second, I want the gradients of this loss function that I want to minimize to be cheaply computable, and by cheaply I mean linear in the dimension of the problem. And so with under the strict constraints, there's not many things that are left practically. What one loss that meets this constraints is what we call in machine learning the reverse scale divergence, which has all these properties. And so this is just to expand a bit how it looks like, and how optimization of this kind of models look like. So these models, they as I said, so they start from some base density, transform them to a target density, and so the target density here appears here at the bottom. If you see this p tilde is the target. And we use stochastic optimization to optimize the parameters that go into the determinant of the Jacobian term. So it's pretty straightforward as an optimization problem. All the complexity comes into having efficient estimators of this determinant. So now, of course, these are learned models, so they will always have biases, or will miss a thing. For example, we miss tails or regions in the configuration space of very low likelihood. So there's no miracle there. Optimization will struggle to capture these aspects of the target. So one thing we can do is try to correct this bias with different mechanisms. One of the simplest things we can do is a simple accept-reject bias correction, where we see the learned model as just a proposal distribution that produce IAD samples, and then we accept and reject them in a Markov chain. A more sophisticated algorithm, for example, is to combine these learned models with more advanced sampling techniques, like annealed Monte Carlo methods. So in this kind of methods, the flow plays a smaller role in that it has to learn only to make a transition from two temperature levels in the annealed chain. So you have in this annealing scheme. So it starts from different inverse temperatures from 0 to the target inverse temperature. And the flow, it only has to learn how to map from one temperature to the next, which is presumably a much simpler job than learning directly the target. So that's the idea of this algorithm. And I don't think it has been applied yet to Lattice QCD, but it's definitely something to keep in mind. Now, just to revise, I will revise the paper that started basically this collaboration, which is the application of masked flows to sampling scalar fields. So this is the paper. So let's start with the problem definition. So once we take the, so all these Lattice QCD problems start from the continuous action, and then you do obviously discretize the differential operators, and you also go to the Euclidean version of the action where all the complex numbers in the action disappear. Well, all the I factor in the action disappears. So for the scalar field, after the discretization, we have this term. So we can identify the Laplace operator there in the middle that has been discretized. You have this the mass term and the lambda term. So now, once you have defined this, the problem that machine learning wants to solve is how to sample phi according to this action. In 2 dimensions, this is a very good match for masked flows using this. So as I said, the masked flows split the input vectors into 2 or more groups and transform them independently. And when you have spatial structure in the data, like a 2-dimensional image or a 2-dimensional lattice, the most sensible splitting pattern is in a alternating checkerboard pattern. So that's what we use in 2D, and also in dimensions is also something that that is used. So this is a illustration of how this flow looks like. You have a example of configuration of the scalar field in 2 dimensions. It gets split into 2 disjoint subgroups that are transformed according to this masked flow, which has a triangular Jacobian, so makes likelihood computation very cheap. And then, of course, we stack many of these transformations with alternating patterns in the mask to increase the expressivity of this model. So this paper provided an encouraging proof of concept that this flow can match quite accurately the results from HMC. So here you can see one of the green functions of the scalar field matched with a very good match between the flow and the HMC results. So this was a very good proof of principle that these kind of ideas work well together. Now this is not the chronological order in which we produce these results, but now we can go from the scalar field to a pure scalar field model to include fermions and see how well we can do when you add fermions to the story. So this is why you got interested now in the Yukawa model. So the Yukawa model, basically we add this extra term to the Lagrangian. So we have the scalar Lagrangian as before, and you add the Dirac term that include with the Yukawa coupling term there. As you know much better than me, the problem of trying to use this out of the box is that the fermions fields that are there, they are not ordinary variables. They are these annoying anticommuting variables. Since there's no obvious way of incorporating that into the model, so a strategy that's adopted in HMC and that we adopt in all our problems is to explicitly integrate the anticommuting variables in the lattice. So when you do that, you get this determinant term. So you get this, once you integrate them, you get an effective Lagrangian that has this determinant of the Dirac operator. But this is also problematic because this determinant is not necessarily a real number. So a trick that's commonly used is if you have two degenerated fermion flavors, so two copies of a fermion fields with the same mass, the determinant is actually now a product of two, and you can show that it becomes a real number. So now that you have this sorted out, of course, this now limits what this thing can do, what the model can do, to having this, always having these two copies of the fermion fields with an identical mass. So that's a limitation there. But now we have a real valued determinant. And the real value determinant can be replaced by ordinary integrals with commuting variables. So that's the idea here. So this mechanism is called the Pseudo Fermions. So these dummy variables that we add to replace the determinant are called the Pseudo Fermions, but they are vector fields. They are not anticommuting variables. They are bosonic variables. So in this paper, we explored the various ways in which we could match the target density. So now we can see this as a joint problem, right? You have a joint density between the scalar field and the pseudo-Fermion field. And we can also see this as two separated problems where you have the marginal distribution of the scalar field and the distribution of the pseudo-Fermion field, which in this case would be just a multivariate, a Gaussian conditioned on the scalar field. And we can also see this distribution in the other order, where we would sample from the marginal distribution of pseudo-Fermion fields and would then sample these scalar fields conditional on that. So we could consider all these combinations of in which order we do the conditioning in the model, and also during the evaluation, this would lead to different ways to evaluate the models. So I will not go to all the combinatorics of this possibility. So I go through only one of the models and evaluation that we consider here. So as I said, so this is just an illustration of various ways in which you can use the models in combination with MCMC to correct the bias of the model as well. So if you have this, we have the scalar field and the pseudo-Fermion fields, then you can sample them in various different orders as well in an attempt to increase mixing rate and increase the convergence of the Markov chain. Okay, just revising what's the target problem at the top. So now we have the this effective action, which which contains the discretized action for the scalar field, and this effective potential that appears after integrating the Fermion part, which is this inverse matrix there involving the pseudo-Fermion fields. In the model that I'm going to describe here is a model that first models the marginal distribution of the scalar field. So it is just a distribution on the scalar field here, which is the phi field. So the var phi fields are the pseudo-Fermion fields. So you have this, it's a flow, so the density is defined in terms of some determinant. And in particular, here I have chosen to talk about a convex potential flow. So as I explained before, this flow is defined by a scalar potential. So its likelihood contains a determinant of a Hessian matrix here. And now, given a sample from the scalar field, we can sample the pseudo-Fermion field exactly by just multiplying Gaussian noise by the Dirac operator, by the discretized Dirac operator. The multiplication by the Dirac operator is straightforward, and this has no problem. What creates challenges in this method is now that we need the determinant of both the Hessian matrix here and the determinant of the Dirac operator. And these two things are quite expensive to estimate. So, and they're not only expensive, but they have their own challenges. For example, the Dirac operator is a matrix that in realistic settings has a very large condition number. So approximate methods to invert it or to compute its determinant struggle with that a lot. So that is a numerical challenge for us here. So we use these stochastic gradient estimators. So in principle, these gradient estimators are very scalable, but we have to keep in mind that yes, there's lots of numerical challenges here with the condition number of the Dirac operator. So this approach is what we call the phi marginal in this table, and it does achieve some very encouraging results in terms of acceptance rate once we plug into an MCMC chain. And this plot is trying to look at the bias of various different observables estimated with different models compared against HMC. So so you can see that the bias are quite promising what these models can achieve in these plots. Of course, this is still relatively a toy setting, but these results, I would say, they are encouraging. So to summarize these results, so masked normalizing flows are a good family of models for 2D scalar fields. We can easily incorporate translational symmetry and the boundary conditions, both for the scalar field and the pseudo Fermion field. So the scalar field uses periodic boundary conditions, and the pseudo Fermion fields use anti-periodic boundary conditions. These things are relatively easy to incorporate in the flows. So adding the pseudo Fermions to the story adds substantial complexity to the problem. As I said, it requires now inverting the Dirac operator and computing its determinant, and these things are numerically challenging. So this is about the scalar fields and the pseudo Fermion fields. Now let's talk about gauge symmetries and how we can build models that have exact gauge symmetries. So first, just to set up the language here very quickly, we have when you say that a function is invariant, right, with respect to the action of a group, is simply that it commutes the action of the group on its input does not change the output. And equivariance, as we already discussed, is when the function commutes with the action of the group. And this is just to set up some notation. So an example of invariant function, a very simple way in which you can build the invariant neural networks with respect to some group actions. So let's say you have this matrix conjugation group action where the matrix U comes from some unitary group. Then I can trivially build an invariant function with respect to this transformation by simply building a function whose features are traces of powers of the input matrix, for example. We use this idea as a building block all the time. So this is one of the key building blocks. Also, as I mentioned before, there's this general result where we can build equivariant functions as gradient fields of scalar functions that are invariant. For example, we can use that to cheaply build the permutation equivariant maps. Sorry. And another set of results that we can show is that if now we want to build now diffeomorphisms in the SUN group, and we have shown that any such a diffeomorphism that is equivalent to matrix conjugation is what we call a spectral flow. That is, it's a flow that acts on the set of eigenvalues of the SUN matrix. And this is very very nice result, because essentially it simplifies the problem of incorporating a continuous symmetry into the problem of incorporating a discrete symmetry. So we want to build something that is equivalent to matrix conjugation. And this result says that all we really need to implement is a permutation equivalent map that acts on the eigen values of the matrices. So this is one of the main tools that we use to build gauge SUN equivalent flows. And I will expand this a bit more. So this is, I just think that this is quite a nice mathematical observation that permutation equivariance is a key to build many other equivariances, including some continuous equivariances. So that's an interesting thing. Another mechanism to build permutation equivariance is what we call canonicalization maps. The idea is pretty simple, not always easy to implement, but the idea is, let's say I want to build the density here. This density has a six-fold symmetry. Let's say I want to build a density with the six-fold symmetry. So what I can do is first implement a canonicalization map that is, it will map each cell to a canonical cell, illustrated here on the right. So I build a map that will map each of the cells into one of the cells. Then I can build any flow I want in that cell and uncanonicalize the map by applying the inverse of the canonicalization map. And by construction, this will have the exact discrete symmetry that we want. So this canonicalization map is not obvious to construct all the time for all the cases, but for permutation symmetry, it's relatively simple to build.
Danilo,
so now, yes.
Just a quick question on the last slide. So you have this cutoff in the vial chamber on this last slide. Are you going to get to why you do that again? I'm trying to remember why there's a cutoff on this non-compact.
Yes, so this, I'll get back to this
Great.
again.
Don't let me stop you.
But if it's not clear, please ask again there. Yeah, because there's a mix of the thing that the computation that's needed, but there's also limitations of the plotting here when it comes to plotting what's going on in the league groups. So, okay, so how can we use these tools for SUN? So we have two papers. One where we start with the group U1, where everything is much simpler, but then we extended these ideas to SUN later on. Before going to back to the groups, so this is just to define the problem. So for the SUN gauge group in the lattice, the action is the sum of traces of little loops, which are called plaquettes, and that's what defines the machine learning problem for us to solve. So these plaquettes are built out of this. So these U variables are what we call the link variables. Right? They are the parallel transport along the edges of the lattice, along the edges of the lattice. And we want to build a flow that works on these U variables. The U variables live in the SUN group or the UN group, depending on which group we use for the gauge symmetry. But the important thing is how these things transform under gauge transformation. So if I apply a gauge transformation to the link variables, they transform according to this rule at the top. Note that this gauge transformation field appears at two different locations in the lattice at the top. Now, if I take a closed loop that starts and ends at a point X, and I transform it, I have a similar rule, except now that the gauge field is the same on both sides. And this observation, this simple observation, is one of the key ideas that we exploit to make to build a flow in this space. So now, because of this property, trivially the trace of this closed loop is going to be invariant. That's how the action is built. So now, if we try to put together these building blocks that we have to build a invariant density on this lattice with SUN variables in the links. The idea is we will start from a simple density. So in this case, we start from the Haar measure on the products of Haar measures for each link, which is just which is essentially just the uniform distribution in SUN. And we use the tools that I described previously to build a gauge equivariant map. And now this gauge equivariant map, from the results that we already have, it will define a gauge invariant likelihood function. So this is just to illustrate what the Haar measure is. As I said, the Haar measure is intuitively the uniform density in the group. So for SU3, if you express the Haar measure in a coordinate system of the eigenvalues, in terms of the eigenvalue angles, right? So the SUN matrix has determinant 1. So the product of its eigenvalues has to be 1. Which means that if you look at the angles of these eigenvalues, they must live in a plane modulo 2 pi. So this is this plane here. So you have is a for SU3, you have this 3-dimensional torus where the eigenvalues live, but they are further constrained by having so that the determinant is 1. So when you express this in the angle space, we have this intersection of a plane with a torus. And if we plot it cutting the rest of the plane, it looks like this hexagon here that I'm showing. And if you just write down what, now if you write down what the Haar measure looks in terms of these angles, it looks like this, and it has this 6-fold symmetry in terms of angles. So this is our base density. So that's the density that we will start from. So this is what we want to build. So we want to build a flow, a transformation F that maps SUN to SUN. So the variable y must also live in SUN. And it must have the property that if I do a gauge transformation on my links, the output of this function will transform exactly the same way as the original links. So that's what we want to build. And as I said, there are a few tricks that allow us to build this. So one of the main tricks is the following. Imagine first that instead of building a gauge equivariant map, we first build a matrix conjugation equivariant map. This is what this thing at the top is. So if you have a diffeomorphism from SUN to SUN, that is matrix conjugation equivariant, as the formula indicates here, then I can build a gauge equivariant map from this map. So the idea is now I can construct the F map by multiplying the matrix conjugation equivariant map by this S variable, which intuitively is an open loop. So the idea is, as I said before, so the things that transform in a matrix equivariant way are closed loops. So intuitively, what we're doing is that we apply the flow to a closed loop, but then you have to open it again, because in the end of the day, we want to transform individual links in the lattice. So you have to multiply it by the complement of that link in the lattice, and that's exactly what this formula is doing. For example, we could this s variable could we could have chosen any other loop that starts and ends at the same points at the appropriate points. It doesn't have to be just a single open half plaquette there, but that's the simplest choice you could make. So now the problem is reduced to finding this map H that is matrix conjugation equivariant. So the reason this problem is much simpler than the original problem, the gauge equivariance problem, is that now the matrices at both sides of the matrices at both sides of the map H are evaluated at the same point. So now we don't have to deal with multiple points in the lattice to build this map. We have to think about what happens at a single vertex of the so that simplifies the reasoning of these things. And previously we have so as I have shown, we have this result that matrix conjugation equivariant diffeomorphisms SUN and the UN and on unitary groups, they have to be these spectral maps. That is, they have to be they reduce to permutation equivariant diffeomorphisms acting on the set of eigenvalues of the UN or SUN matrices. So mathematically, that's just what I said here. So if you have a UN SUN or UN matrix U, we can start by doing an eigen decomposition of this matrix and apply a permutation equivariant diffeomorphism to the set of eigenvalues here, and then stitch the matrix back. So we have shown before that every matrix conjugation diffeomorphism is of this form. So we are not losing any expressivity by doing this construction. So that's the idea behind this. And now the challenge is, okay, how do you build a permutation equivalent map on the eigenvalues of an SUN matrix? So as I mentioned previously, because SUN matrices have determinant 1, the eigenvalues are constrained. So they do not live just in a torus, they live in the intersection. So if you express this in terms of the angles, so the angles live in the intersection of a torus with a plane module 2 pi. And this is what we show here in the middle. Now we want to put a density that is permutation equivariant or permutation invariant in this space, which is the intersection of this plane with the torus. And we adopted the canonicalization map strategy. So for SU3, first a general comment, maybe this is related to Jim's question. So for SUN, if you look at the tangent space, so you see that any invariant density, any matrix conjugation invariant density will have this n factorial fold symmetry, where the density will be copied over this n factorial cells. And for the group SUN, the cells, they are simplexes. There are simplexes for which we can compute explicitly the coordinates of the vertices, so we can build explicitly a flow in that space. And to incorporate the symmetry, we use the canonicalization map idea. So we map each one of these n factorial cells into a single canonical cell. Then you build a flow in this simplex, n-1 simplex there, and then we uncanonicalize back to the full space. I don't know if that
Just to make sure I
clarifies your
understand, yeah. I
question.
mean, I think you're basically saying that the compactness of the simplex rather than the non-compactness of a Weil chamber is coming from the exponential map according to the
Yes,
yeah.
yes, exactly.
That's what compactifying it.
Yes, exactly. So because this, yes, because this plot is a bit confusing because the density is in the torus,
exactly.
is in the actual group, but the figure is in the tangent space, is in the Lie algebra.
Yeah, I think that's why I was getting confused. The theorem you quoted earlier relates the diffeomorphism on the group to the diffeomorphism on the maximal torus. You said
yes,
right?
exactly. So
indeed in the group, not in the algebra.
So the Weil chambers, they are these infinite cones, right? And
yes.
but when we do the exponential map of the Weil chambers, they become the simplexes in the projected when you project right. In the torus.
And I guess your point is I never in my brain should have passed to the Lie algebra in the first place. I should have just stayed on the maximal torus, and then you have these simplexes.
Yeah, exactly. So it's just this draw is easier to make the figure in the tangent space than in the actual 3D torus. So it kind of brushes over this projection part, but the density is defined in the group in the maximal torus. That's where the density is defined.
Absolutely, I'm with it now. Thank you for the clarification.
Okay, so there are a few more tricks to how to build a normalizing flow on an arbitrary simplex, but this is relatively simple. We blow up one of the vertices of the simplex to convert it into a box. And now building flows in boxes is a much easier problem. For which you can use off-the-shelf like existing normalizing flows, and then we can map the box back to the original simplex. So that's the original idea. So when you put all this together, it looks like this is onion of layers. So for every link variable, we do an eigendecomposition. Do this canonicalization step to map all the angles of each eigenvalues back to a canonical value chamber, and then build this simplex flow there, and then uncanonicalize, and then build the matrix back, and then that's one transformation of the lattice configuration there. So this is just to illustrate this project the chambers for SU2, SU3, and SU4, how they look like. In SU4 have a 4 factorial symmetry. So yeah, so this is just to summarize what I just said, that for special unitary groups, these equivalent flows reduced to build a flow in a simplex. That's what will reduce the problem to. And if you look at from a bird's eye perspective, this is how the flow looks like. You have just these steps I just explained in this stack. And this is just one block of the flow. Now we stack several of those to build a more expressive transformation. So this so that's the idea of this pure gauge equivariant flows. So if I introduce some special notation, I can make it look a lot more simple than it is, a lot simpler. The idea is if I use a diamond to indicate a matrix conjugation equivariant map, and just some notation for a matrix product, this whole flow can be written in this very simple notation, and can be graphically illustrated this way. So if you think about what the flow does on a single link, let's say this red link here, first we multiply it by another open loop so that we build a closed loop. Then we know that closed loops are matrix conjugation equivariant. So we apply the matrix conjugation equivariant map, diamond map, to that, and then we remove the rest of the loop again from the transformation. So we have something that transforms as the original link again. So that illustrates in a simple way what's going on. And then, of course, the flow does that in parallel for all the links simultaneously at every step in every step inside the model. This is just to illustrate some of the results from this new one model. So the nice advantage of the flow, which we hope to carry over to more realistic scenarios, is this mixing. So when you build the MC Markov chain here to sample a topological charge, which is something that can be hard to sample with HMC-like methods. So we see immediately see the advantage of the flow here. So if you have an HMC, so we see, here we're just seeing how the HMC chain is going around different values of the topological charge. So this gives an idea of the mixing, how the mixing of these variables is happening in the Markov chain. Where samples for the flow, they're all over the place in the space. Maybe they will miss the long tails, but in the bulk of the density, they have very nice mixing. So that is an encouraging result. It's still, disclaimer, this is still very toy regime, but encouraging still. Now, this figure is just to illustrate that you can learn some non-trivial densities on SUN for n is larger than 3. So, so here you can see SU9, and some of the collaborators even have results for SU100. I don't know if that has any practical relevance, but we can do it. We can build SU100 invariant densities. So there is also a tutorial if anyone is interested in replicating some of these results or just understanding at the code level some of these ideas. There's a tutorial online. And now I just want to conclude with some generic discussions about what we need now on the modeling side, on the flow side, to include fermions to this. So the strategy that we can follow is very similar to in the case of a Yukawa model. We can just add this the effective potential that comes from integrating out the fermion fields in this model. So if we're working in 2D, this is the Schwinger model, where I have the lattice gauge action plus this extra potential that's coming from the Dirac operator there. But now, if we consider the set of transformation rules with the fermions, there are a lot more combinations, obviously, because we have now to account for how the pseudo-fermion fields transform under gauge transformations. So when you build a model, if you want to build a model that's equivariant with respect to the gauge transformation, it has to incorporate both how the gauge field transform and how the pseudo-fermion field transform. And that increases a lot the combinatorics of the model. This is just to illustrate, for example, in a pure gauge model, gauge invariant quantities are traces of closed loops. But now, in the model with fermions, we can build many other different gauge variants that mix up the gauge fields and the pseudo-fermion fields without necessarily building closed loops. And we can think of the simplest possible instantiation of a masked flow that has these properties, which is as before. So we can build a flow that transforms, as we did for the Yukawa model. We can build a flow that models the marginal gauge field, like we model the marginal scalar field. And now, given that, build another transformation that models the pseudo-fermions conditioned on the gauge field variables. and a masked flow that would satisfy that would have the right equivariance property for the pseudo Fermion field would look like this. So if you want to build linear combinations of the pseudo Fermions at different points, in order to preserve equivariance of the linear combinations, you have to do this parallel transport of the pseudo Fermion fields back to a common point. So that the parallel transported fields all transform in the same way. Otherwise, we lose the equivariance because each term in the linear combination will transform according to in a different according to gauge the gauge transformation field in different points in the lattice. So we have to, but after we do the appropriated parallel transport, then the parallel transported fields will transform all in the same way, and you can just add them or do linear combinations of them. So that's what this term here is doing. So if I build, if I have gauge invariant weight factors, then it becomes trivial to build like equivariant linear combinations of these fields. So this is one way to combine masked flows with all these properties. And to build this gauge invariant maps, we also know how to build that. For example, we know that we can build the gauge invariant things as trace of closed loops. So we can take various closed loops and pass their traces as input to the neural net. And we can also build the gauge invariant quantities that mix up both links and pseudo Fermions in the appropriate way. Basically, you have to multiply open path by the pseudo Fermions at the starting and ending vertices of the open path. And this is also a gauge invariant quantity that we can pass then as inputs to this transformation. So to summarize, so there are many challenges of this of doing this. So we can construct flows that have built-in UN and SUN gauge symmetries. We have these results in 2 dimensions in the string that are quite promising. We can also extend the idea to pseudo Fermions in the same way as we can do for the simpler Yukawa model. And as for this Yukawa model, the pseudo Fermion ideas add substantial complexity to the modeling. The same problems appear again. So this Dirac matrix has very large condition number. And now we have this extra problem that we don't have in the Yukawa model, which is there are many more quantities that are gauge invariant and the gauge equivalent that we can build. So there's this kind of combinatorial explosion of ways you can build the model. And finally, just wanted to mention that there are some, as you can imagine, intrinsic limitations of this pseudo Fermion approach. It seems to me quite a strong constraint that you have to always have these pairs of Fermions with the same mass for this approach to work. But generalizing this is for now beyond the scope of the project. We want to push the limits of what can be done in this regime. And there's still a lot to be done, especially in the Schwinger model. And as you go to less toy configurations, when you have a 3D and 4-dimensional lattices as well. So there's a lot that we can try there. And that's it. So stay tuned for upcoming work if you're interested. And thank you for your time.
Excellent. Thank you, Danilo, for the wonderful talk. There was a lot there across a broad spectrum of topics, and it's really beautiful work that you guys are doing. And I see a number of your collaborators in the audience, friends of mine too. So that's good to see them.
Yes.
I'm sure there are many questions. Please, if anyone has a question, feel free to actually just unmute yourself and ask. So maybe while they're coming in, I'll start with a question that you were mentioning, this canonicalization map and the permutation invariants. So to generalize to other groups, I think you told me at some point, we talked about this like a year ago, that there's this issue of finding the vertices of these simplexes, and that's part of the hard problem and how that intertwines with the canonicalization map. But if you were able to find that canonicalization map, and I guess the point is you won't have you won't have permutation being part of the story anymore, because that's the Weil group of SUN specifically. But if you could do it, if you could use the Weil groups of the other Lie groups and then find those vertices, is there any reason that you can't just do this for any simple Lie group?
No, in principle, no. So if we can explicitly compute the Weil chambers, then basically these cells, they are the exponential map of the Weil chambers. And you have this, I think we also discussed this at the time. So you have this as the Weil chamber, with the exponential map, they wrap around the space, they will meet each other, right? That's where you get the coordinates of the that's where you get the coordinates of the vertices, right? Because the Weil chamber extend infinitely, so as you project them, they wrap around the torus.
So finding these intersection points on the torus are crucial to determining the structure of those cells.
Yes, but so this is a mechanism that we found that I think is very effective for SUN, but maybe for other groups, I'm now tempted to say that maybe there, if you go for one of these more general flow ideas, where, for example, this cost convex flows on SUN. For example, SUN, we know the intrinsic distance exactly, so we can still build this kind of, we know the exponential map, we can cheaply compute the exponential map, and it's Jacobian there. So this kind of flow would provide a much more generic mechanism that that you don't have to dig into the eigenstructure of the matrix. So the result we have says that whatever flow you build that is matrix conjugation equivalent is a spectral flow, but you don't have to build it explicitly like this. So we basically build it like in this very constructive manner. But if you build this cost convex flows using gradients of matrix conjugation invariant potentials, then it also has this property, and it'll be a much more generic construction that's not specific to SUN anymore.
I see.
But then I don't know which other groups if you have. So if these other groups that you have in mind, if you know exactly the exponential map, for example, you'd have to know that exactly.
Yeah, I mean, it definitely becomes a problem for other groups. Like the Weil group of E8 has, gosh, the order is like 1 million or something. I don't know. It's rather large. It's a rather large
so
number.
You have, I don't know if you have a closed form for the exponential map, and also the the other thing we need is the intrinsic distance as well, which may be tricky in general.
Yes.
So,
No,
for this kind of flow, you need these two ingredients. If you build, instead of building this cost convex flow, you go for this Riemannian ODE flows. It's a bit more relaxed there, because there you don't need first you don't need this cost convexity. You just need the scalar potential that is invariant there. But now you have to go through the pain of integrating an ODE in this manifold. So you have to put like charts. Integrating all these in manifolds is just a pain. You have to create these local charts and keep updating the metric in the charts as you go along the integration. So I mean, there's lots of literature on that. You can maybe just use an off-the-shelf integrator there, but it's still numerically it's quite involved to do that. But if you're willing to pay this price, then you're a lot less constrained in the model side. So you just build a scalar function that is invariant to the action that you want, and that should already work there. So there, as you can imagine, there are many trade-offs with these ideas, right? So
yeah. No, excellent. Thank you for the additional comments. That was great. I, of course, have more questions, but I'll give other people a chance to ask if they're out there. So, Does anyone have a question for Danilo?
Yeah, actually, I guess so. Obviously, the computational cost of including fermions makes everything just a lot more complicated. But I was curious about, I guess maybe the comparison between training with the inclusion of fermions versus just purely for the gauge fields, as well as I guess like overall kind of, but also like what that factor might have been after including fermions.
So I'm not sure if I understand the question. I want to understand what's the difference in terms of the computational cost of training in the pure gauge and the pure gauge plus the fermion term.
Yeah, exactly. That's basically it. Just how much harder is it to train when you include fermions?
Yeah. So in order to compute this effective potential that appears from the pseudo fermion potentials, so this is it's a Gaussian essentially on the pseudo fermions. They are Gaussian distributed, given the scalar field in the UCAL model or the gauge field in the gauge models. They are just Gaussians in theory, but this matrix that's inside contains the inverse of the Dirac matrix. And what makes it hard is that the Dirac matrix has very large condition number in the realistic settings. So this inversion, so for example, if you use CG, it may not converge, or it may take many steps to converge. So just to evaluate the action, you have to invert the matrix. So in the regimes that we are working on, standard naive CG still works. It can struggle in some regimes already, but you can still use it. But in a realistic regime, in more realistic regimes, we have to use a lot more, much fancier methods to compute this term, basically. So in a more realistic setting, you have this like multi-grid methods or more advanced versions of CG that are needed there. But the cost is essentially the cost of training is essentially the cost of inverting the Dirac matrix using CG, basically.
Yeah, that I guess that makes sense. That's really always going to be the main bottleneck in any of these kind of approaches, I suppose. So that, yeah, that's fair.
What is the bit positive side of this is that the Dirac matrix is itself is a quite simple matrix and very, very sparse. So the CG is a really good match to that because we implement in a sparse way. But still, what makes everything really hard is the condition number of this matrix. Yeah, that's a very large number. So this makes
that makes sense. And then by doing that, you can utilize any of the existing tools and tricks there are for converting it and things like that.
Yeah. Yes, there are many tricks from the Lattice QSP community, of course. This is problem that is not that also plagues HMC, not just our model. So there's lots of stuff that people have tried and improved. So we are not using any of the fanciest methods to invert the matrices yet. We tried somewhat more less trivial ideas in the paper in the UCAL model. There's this even odd projection that produces the condition number, but still, it's a bit tricky. It's still there's still a lot to improve there on the side.
Any other questions for Danilo? I missed something basic about the pseudo fermions because I've never studied them. They're modeling the Dirac fermions specifically. Is that right?
Yes. Yeah. So in the UCAL model, so you have these staggered fermions, which are the staggered fermions, where it's a particular basis that you work on for the fermions that simplifies the actions. Basically, you do a Lorentz transformation that diagonalizes the gamma matrices. So that's the staggered fermion. And but for the gauge fields, we work on the Wilson terms, which is the different way to discretize them.
I see.
To discretize. So there, when it comes to the direct action, there are many different ways to discretize it, and each one loses something about the continuous, loses some aspect of the continuous model. Right? They create these spurious modes that different discretization schemes try to mitigate. But yeah, so there are many different discretization schemes.
There are different discretizations of Dirac fermions in the continuous model.
Yes.
Yes, absolutely. Good.
Yes.
Good. Which, you know, for QCD is what we want. So that's great. Wonderful. Yeah. Well, I have other questions I want to think a little bit about before I ask them. But is there one more out there for Danilo, or I always try to pause to give people time to get up their courage. All right, well, in that case, I'd like to thank you one more time. I'm sure others out there feel similarly and can express their gratitude with various reactions. I'll do it myself. Thanks so much for the great talk. It was wonderful to hear more about your work, and it's exciting that you and your collaborators are continuously just pushing on each different aspect of Lattice, sort of moving more and more towards you know, the cases of most interest, and it's beautiful stuff.
Yeah.
Thank you very much, Danilo. I'll
Thank
stop.
you very much.